derivatives of parametric equations, or the slopes to parametric curves. The slopes to parametric curves, dy dx and d squared y over dx squared. That's endeavor number 2. And that begged the question, what was endeavor number 1? And so I showed you. Endeavor number 1 is going between polar and parametric. Okay, now we're good? Okay. We need to get deriving and having some fun, huh? Okay. No, why not? Oh, nap. I thought you said, can we not? And I was like, oh, well, no. Okay, section 4.2, you guys ready? You guys teach me what's the difference between implicit and explicit. I don't disagree with anything that's been said. Keep going, though. There's more. And where I would go. That's kind of where I would go. Why does Maggie's not fully encapsulate implicit and explicit when she says there are two? There's a y and x in both of them, yeah. Okay, and then Riley said, forgot. Isn't in standard form, but then she didn't explain standard forms. Then Aryan kept going and said, y by itself versus y not by itself, right? So either y is all mixed up, he's all mixed up in the struggle. This one, y is isolated. True? Now, here's a better, not a better, but here's another way of thinking about it. Wouldn't explicit always be functions and implicit very possibly could not be? Why would it be easier to have a non-function implicitly defined versus explicitly defined? What am I talking about? Yeah, it does look nicer instead of having a square root and stuff, but why are these almost always going to be functions and these very commonly not functions? How would we know whether or not these are actual functions or not? Yeah, but graphing, you're going to have to get y by itself. Good question. Functions. Let's go back to Algebra 1. Like literally. So what are functions? You're thinking. What are functions? Oh dear. We've gotten too high. James, what are functions? So each x, one and only one y. The simple way of testing it is passing the vertical line test. Because if you ever hit an x value, which is a vertical line, that connects at more than one y, that would fail the qualification for each input has only one output. Okay, so why could non-functions, aka relations, ooh, that's going back, right? How could non-functions show up more easily implicitly than explicitly? What's function notation? Instead of saying y equals, we say what? Function notation is built upon y being by itself. F of x equals like y equals. Implicit, hold on, let's just think of the easiest one. What's the easiest? I was going to say function. The easiest, I can't use the word function. Graph, relation, equation. That fails the vertical line test. What's the most common one? I would think this guy. Right? Does he pass the vertical line test? But he's so basic. He's just a sideways parabola. What's the equation of a sideways parabola? X equals y squared. Oh! What's another one that fails the vertical line test? What's that equation? X squared plus y squared is, what's in common between this and this? Y isn't alone, but not only is y not alone, y is also to the squared power. Oh, hey, he's not a function. What does that mean? At one x value, you might have more than one derivative. Oh, how could you have more than one derivative at one x value? Because you have more than one point, and those points will have unique slopes. Does that make sense? So anyway, implicitly defined. How can you define non-functions? Implicitly, or using parametric equations. You can have non-functions and parametric equations also. Anyway, because if you guys have ever wondered, it's impossible to graph a non-function using your y equals menu and just using one y. Now we can use like plus or minus square root to cheat and like put two together and pretend like it's one. But our entire calculators and the entire graphing feature is built upon, in function mode, only graphing functions. Anyway, putting a few things together, but let's go ahead and come down here. Boop, boop, boop. How can we take the derivative of an implicitly defined function, relation, equation? Anyway, an implicitly defined thingamabob. How do we take a derivative? We have to keep in mind, whenever you take the derivative of something in terms of y, with respect to x, we need to think of chain rule. So what would be the derivative of f of y with respect to x? F prime of y times, you could think y prime, which is what we put or write as dy dx. So we have to remember the dy dx. Long story short, because you're taking the derivative with respect to a variable other than what you're facing. Okay, that's more familiar, right? So if you want guidelines, and if you don't want them, still review them. How do we do implicit differentiation? To find dy dx, well, we need to eventually get dy dx by itself. But the problem is, if y is not by itself, how are we going to get dy dx by itself? Take the derivative of everything that you have, both sides of the equation, collect all the dy dx's on one side to factor him out to solve for dy dx. And you guys have gotten a lot of training, those of you that have went through AB. You've gotten a lot of training on this, so it shouldn't be as bad. But at the end of the day, you do need a dy dx isolated, but this side should be implicitly or explicitly defined. How is it possible for dy dx to be by itself but be implicitly defined still? You could still have x's and y's all mixed in. Good. And if you have x's and y's all mixed in, how would you plug in a point for a particular slope? Plug in the x and the y. No big dealio. When could this get tricky? Some of you are writing this down totally fine. So let me show you when this could get tricky using a pre-cal example from today. Pre-cal, going back there. Ooh, I thought I had it. Something like that. As you guys are writing the guidelines for the rest of you that are chilling, the reason or when this can get hard comes straight back to, besides chain rule. Of course, chain rule can get hard. You guys can make mistakes. But coming back just to this, the other way this can get hard is just in the algebra. The algebra gets tricky on this problem. When I ask the pre-cal kids, solve for an inverse. Why? How do you solve for inverses? Just review basic math. Switch x and y, solve for. Why don't they like this? Why is it hard? Doesn't it make it look almost harder when you multiply? Why did all the pre-cal kids get really, really stuck? So they start trying to like divide by y's or to like divide by x's or do crazy stuff that doesn't help, when really all they should have done is
distribute and then move the y to the other side and then take y out and then move everything over by dividing.
Is it possible to get y by itself? Was it easy? No. Why wasn't it easy? Because you had to do some of this like, oh, division, ew, multiplication, ew, distributing, everything's looking worse. Wait, here's where it connects. We're trying to undo all the multiplication, all the division to get separate terms, because then can't we collect all the terms with y's on one side, factor out the y, and solve? It's the exact same idea as here. As long as you can do chain rule correctly, we're just trying to get all the terms with dy dx on one side so we can factor out the dy dx so that we can solve for it and get it alone. So, boop, boop. Ready, set. In your groups, go. Green highlighter. Ready, set, go. As we can tell from section 4.1 homework, we tend to make mistakes, so maybe check yourselves along the way so you don't get to the end and then realize you messed it all up. The yellow highlighter. Blue highlighter. I have green markers. I think it might be dead too. James is looking, maybe. I have green things that would not highlight nicely. I would try to leave it as factored as possible. But if there is a distribution, like you would. Check in. Maybe you already made a mistake. Just check in, make sure everyone's on the same page. Naomi, we have a new submission. People who aren't checking in, we're on the right track, right? We're sure? Can I play? Ariane, there wasn't an easy answer to your question because it all depends on where it comes up. Does that make sense? Pause. Did you get your dy dx's in the right spot? So in the chain rule, in the part where it applies, it does get multiplied. Well, derivative of x squared is 2x times x prime is 1. Derivative of y squared is 2y times y prime, which is dy dx. So it doesn't get distributed to other portions of the function where the u prime didn't apply. Oh. Right, because you can't make this u. This is a u, right? It's 3u squared, which would be 6u times u prime, but u prime would, in its own parentheses, just have 2x from the sum and difference rule, 2x separately from 2y dy dx. So this is a u, this whole thing is a u prime, but this can't go beyond because you have two separate terms you're deriving. Does that make sense? Sorry, Jessica. Yeah.
Yeah, okay.
Right here, right?
Yeah, and like here to here. Like really, like when I started multiplying everything. Because I just don't want to go distribute it correctly.
You forgot your 6. Because your 6 is going to be a part of both. So you needed a 6 right in there.
Okay.
Does that make sense? But then, Aryan, there is a big distribution about to come with the plus, right? Because of this guy. How could you not? You could technically. I was trying to give it some, give the people that kept going a place to check. But yeah, that was what I was about to do. That's what I'm about to do, I should say. Any of you guys struggling with getting dy dx by itself? And some of you that are you a little discouraged now that you just heard Maggie say, why don't you plug in right away? Problem solving trick. Step 1 here, yeah?
That's how you, like, that's right there, that's how you get it all wrong.
Mm-hmm.
That's called
And waste time on the AP, right?
Yeah.
But our answers should match, right, Maggie?
I can't count. Oh no, the bottom will. It'll be fine. And she's fine. Oh, no, because it's a negative.
How did Maggie and Riley get 13 over 9 and they've been chilling for the last like 5 minutes? Back here they were like, oh hey, you have the 0.31. Why don't you just go ahead and plug it in? And wouldn't it have been way, 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 way nicer? Especially on like an AP where you're trying to save time. To go ahead and just plug in and say 6 times 3 squared is 9, 9 plus 1 is 10, times 2 times 3 is 6, 6 plus 2 times 1 is 2 dy dx. Why is it so nice if you can just go ahead and plug in? You don't have to worry about all the craziness of dy dx's because look, they just have little numbers. So you can go ahead and have 60 times 6, which would be 360. 60 times 2, which would be 120. It's a lot easier to get dy dx by itself if you just have numbers. But you can only do this shortcut trick when it says find at a point. If they just said find the slope, wouldn't you have to end here? Oops, here at dy dx equals. If they say to plug in, you can stop way back here and just plug in check. If they're asking for the general derivative or the entire derivative, you'd have to come down here. Which, sometimes you can like change this drastically to look differently based on the original clue, but I don't see the original clue matching up anywhere. There's no x squared plus y squared squared. So there's no easy way to do any like crazy substitution to make it look differently. And we'd end up with subtracting 300, negative 180. dy dx equals negative 260. dy dx is equal to 13 over 9. Looks like a not equals. Lo siento. Boop, boop. It looks like a little not equals, like it had a slash. Because I was nautical. Nautical miles? Ooh. Knots. Anyway. Questions. We okay? Okay, remember, when do you put a dy dx? When we feel like it? No, so you describe to me, because I always describe it. It's your turn. How do you know when to put a times dy dx when you're taking the derivative of something gross and nasty like that? Not whenever you see the y, because check it. Yeah, whenever you're taking the derivative of something that's not with respect to, or not in terms of the variable that you're taking the derivative with respect to. So I was taking the derivative of y, so 1 dy dx. I was taking the derivative of y squared, so 2y dy dx. Just because there's a y doesn't mean there's a dy dx. And plus a differentiation. How about for the second derivative? Ooh! How about the second derivative, not the first? We just practiced that one. D squared y over dx squared. Find dy dx, take a d dx, and then plug in dy dx? What do I mean? Well, you guys, go. Nice thing is I made them a little bit easier, though. Find the second derivative. You're welcome. It is up to you as to whether you get dy dx by itself or not. Maybe you want to experiment a little bit. Is it easier to not get dy dx by itself? Deriving again? Maybe you just take the derivative implicitly before getting dy dx by itself? Trying to let you get a little bit ahead of me.
Is it first D second or second D first?
We do second D first plus first D second, because then it's bottom D top minus top D bottom. Both ways work though, because it's addition. So I do second D first. Oh, so if you want to check the steps, then yeah, do first D second. Just be careful, make sure your quotient rule is the same no matter what. There's no switching quotient rule. You guys are going, right? So I can go?
Wait, isn't the derivative of 8 0? It like screwed up the whole thing.
Good job. That makes it a lot nicer though, right?
Yeah.
Where am I going? Oh, I haven't taken my derivative yet.
Just get rid of the 8.
Oh, from the beginning. It's a struggle when I start making students common mistakes. Struggle.
Yeah, can we just take it to the end?
Not yet. But now when can I? Yeah.
You have made y to the negative 1 power.
Oh, I'm such a... I just cancel this 6.
Yeah, you could. You could.
I kept the 6 in and my answer is so complicated for no reason.
How different? Can you make it match? What? So what do I mean by the other variation? The other variation would say, instead of getting dy dx by itself, instead of getting all the way down to here, couldn't you technically do d dx right now? What would that do? That would give me a 12x minus, what would I have to do here? Product rule. If you did it this way, oh my goodness. Second, d first plus first d second.
Yeah. I don't know about that. Yeah.
I'm not saying it's necessarily easier, but it is another variation. Then you could have that equal to the derivative of would be 0. Does it work? Yeah, because then you would go ahead and what? Subtract the 12x all over. Subtract the 12x, add the 6 dy dx squared all over 6y. Why is this not necessarily easier, though? Even though I could get this alone.
Square the dy dx.
I would have to square the dy dx, but coming back, hold on, how can I square the dy dx if I haven't even gotten dy dx by itself? So why do we do this? Why do we get dy dx by itself first, even though we could just keep on going implicitly? We're going to have to plug in dy dx anyway, so may as well get dy dx by itself and then go ahead and have it ready to go, as opposed to having this mess with notation that gets confusing. There you go. So I don't like the other variation, but I'm just letting you know it is an option. You could technically do that. And then when you take the derivative of the derivative, you get the second derivative. But you would have to come back, get dy dx by itself, plug it in, simplify, blah, 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 yucky. Okay. Oh, hey, done. You guys want to write down homework? Okay. Homework? Yeah. Can you what? Yeah. Did I have 2 people talking to me? I heard Diva. What were you saying, Maggie? Yeah. It's in the little boxy thing. Classwork? Where are we at? Homework 11? Okay, let me freeze the screen. You guys can go ahead and write it down. Let me pull up page 170 because we still have like 10 minutes. Go, team. I suppose we should keep going, but I already bumped the calendar a whole day instead of like a partial day, so. I know. Yeah, 4.2. At least a few of you guys had busy nights tonight. What page are we going to? 170?